We are all very clear about the meaning of the word computer. There is no danger of getting confused with other objects. A computer is anything that goes to internet, if it's smart. It has apps. It performs complex calculations, it has graphics, video, databases. It has an operating system, like Windows, iOS, Android. All aspects that make us think of a computer without any doubt. We use these machines in an infinite number of situations, often without even realizing what we are using a computer. The smartphone is certainly the computer with which we all interact most often. But also the PC is a tool that we all use on a daily basis. As with the car, we are all able to drive it, we know the traffic rules, we know how to use the steering, how to start it. But few of us are able to change a tire, or change the oil on the engine. And if we can put our hands in the bonnet, then we are technicians. But how many are able to project a car? This is a skill that rightly belongs to engineers. We receive advertising messages for new car models that consume little energy, that have exceptional performance, but the designers of those models really know the technical efforts that have been necessary to improve performance. Beyond the advertising slogans, they could explain us what technological innovation consists of and how deceptive the advertising messages are. How can you avoid being fooled? Not to believe this or that thesis. How do we know what's real and what's advertising? We can't all become car engine designers to defend ourselves against false information. The purpose of this presentation on computers is to provide you with all the information that computer technicians have, without forcing you to study to become a software architect nor a programmer. It may seem like an unattainable goal, but I assure you that at the end of this presentation, you will realize that you know the computer like the back of your hand, without being a specialist nor a technician. And in this way you will be able to understand what data processing, graphics, videos, the famous artificial intelligence, and all the future implementations that may arise from the world of computers consist of. We will use a particular approach. We're going to go over a number of very technical topics that might put you off, because they are certainly not things that will interest you directly. We'll tell you first. The purpose is not to make you study computer science, but simply to let you discover how things work in the world of computers. You listen, but don't worry about having to understand. The few things we are going to tell you are enough to leave you with the right impression of what computer science is and how it works. Let yourself be carried away by this long story that I will try to make pleasant and interesting. Every now and then a slide will appear with a blue background that will serve to take stock of what I have told you so far, and what you need to fix in your mind to continue in the rest of story that follows. The blue slides are the ones that fix the key points that deserve your attention. Let's start. Let's start fixing our ideas on what we are used to consider electric, and what we consider electronic. We take stock of the differences, even if we have to dust off old information from our school days. The light bulbs, the stoves, the ovens, the school bell, the motors are electric. Perhaps not many of you remember that when it comes to electricity, at school we talked about resistor, capacitor, induction, or coils, and of course we all have a clear idea of what batteries are. We are talking about objects that are part of electrical engineering. If we think of radio, television, and computers, we think of electronics. Why? What's different about these objects? They make extensive use of a particular component, the transistor. In electronics, there are also diodes and LEDs, but we will focus on the transistor. Let's say right away that the goal of this presentation is to lead you to understand what a computer is and what it can be. It is not an easy thing, and for this reason many statements may not be correct from a formal point of view, but if they are approximate, they are functionally so, to make this long roundup of news easy to digest and pleasant to follow. Therefore, from now on, we want to start by saying that we are perfectly aware that many explanations should be revisited and corrected from a formal educational point of view. Those who want to learn more can do so separately, where they will surely find all the definitions explained in an impeccable way. I remind you that everything that will be explained in this presentation does not necessarily have to be studied as you would at school. This is not a lesson on computers, but a roundup of technical notions, which you certainly do not have and which are told to you for the sole purpose of putting you in a position to understand what this machine that we call electronic brain, computer, artificial intelligence really is. So don't worry if what is described is objectively very technical. Move from one slide to another as you would visit any museum, without being an expert on the subject, but just look and listen, and if something intrigues you, even better. Let's talk about the transistor. It is made up of 3 layers of silicon, or germanium or gallium. The middle layer is called the base and is graphically identified by AB. The outer layers are so-called doped by p-type atoms, boron atoms, or by n-type atoms, the nitrogen-type atoms. It is therefore customary to speak of PNP, or NPN-type junctions. We don't care much about all this, but it's the premise for focusing on how the transistor works, which we'll see immediately. Let's focus on the image below. A transistor is pictured. If between extremes B and C, you enter any wave, imagine a sound, or a music, or a voice that speaks. On the other side, between E and C, you get the same waveform amplified. If we look at the graph at the top left, we see that the ratio of everything that goes in, I mean the smallest waveform at the bottom, is perfectly proportional to everything that goes out, I mean the same larger, amplified, outgoing waveform. That means it's a great transistor, class A, that's suitable for amplifying sounds and building a quality hi-fi system. But this is not always the case, of course. There may be lower quality transistors, less expensive, which still amplify sounds in an acceptable way. We will be using them in other devices where absolute sound quality isn't as critical. Now let's go back to this image below. A new transistor is pictured, this time definitely not suitable for amplifying the incoming sound. In fact, if we inject the same waveform as before, we get moments in which a lot of current passes through and others in which absolutely nothing passes. Nothing to do with the input waveform. So absolutely useless as sound amplifiers. Now let's look at the graph at the top left. Unlike before, the response of this transistor is no longer linear, it is an exponential curve. In practice, in the face of small variations in current, practically nothing happens. Then once a certain threshold is crossed, everything passes. It's definitely not a linear answer, but that's how we found the basis for building a bit on-off, the element on which all information technology is based. Let's make it clear right away that even a single bit requires a minimum of electronic components and a circuit that is not really simple. As you can see, if I press the S set button, I generate a pulse current that causes the LED to light up and stay on, to indicate that the bit is on. If I then press the R button, reset, the LED goes out and stays off. Because, in order to use the bit, I need that in the face of an impulse, such as pressing the key, the bit turns on or off and remains in that position until a new pulse occurs. Hence the need to build a circuit with 2 transistors and some electrical components. As we will see shortly, I need a lot of bits, and therefore we will have to wait for the industry to be able to miniaturize these circuits and produce the so-called chips in order to have so many bits in a small space. Yes, but what do I do with bits? Well, I do what I already do with 10 fingers, I count. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I do calculations. 5 plus 7, 12. I do all the calculations I want. And with only one bit, how do I do? I count as if I have only one hand with only one finger. 0 is 0 and 1 is 1. But then for the 2 I help myself with another hand with one finger, and I write 1 0, which does not mean 10, but here it becomes 2. The 3 becomes 1 1. On the 4 you need 3 hands with one finger, and it becomes 1 0 0, and then 1 0 1 for the 5. 1 1 0 for 6 and 1 1, 1 for 7, and so on. I do the same with operations. 1 plus 1 gives 0 with the carryover of 1. 0 plus 1 equals 1 and the other one I reported equals 0, and I report 1 again. And so on. If you look at the result of the sum 1100 and compare the list of numbers at the top, you will find that 8 corresponds to 1000, and 4 corresponds to 100, which added together makes exactly 1100, and that is 12. It is not easy to learn binary arithmetic, the arithmetic based on bits, 1 0. But don't worry, it's not important for you to know how to use binary numbers. We have talked about it only to draw your attention to the fact that the computer is born and thinks around the bit. Only 2 values. 0 and 1. This is something you need to notice and make your own. This is a key, a very important point, and we will see it in a little later. The industry is already miniaturizing circuits, and the first integrated chips are being created that contain more and more bits. For now, let's think about the bits to be used to store numerical values. Then we will see how to deal with data, information of other nature. With integrated circuits, we begin to talk about RAM, random access memory. I mean the ability to have many bits available and to access them dynamically to analyze the content of this, or that sequence of bits. We have seen that with bits we represent numbers and on numbers we can make calculations, but first of all let's give a solution to this problem. Before completing any arithmetic operation, how do I know how many bits I need to represent the result, if I already don't know the result? Solution. I treat bits in groups of 8, a multiple of 2. This is how the byte was born. Memory addressing is done in groups of 8 bits, this is bytes managing. Therefore, to identify a datum, I mean a sequence of bits, you just indicate the position of the first byte, and the number of bytes, the length. For example, a datum that begins with the byte at position 3907 is addressed by indicating 3907 as the beginning, and its length in bytes, which in our example is 6. The bit content we use can be lower, 6 bytes could be even too much, but it doesn't matter. The sequence of bits we are interested in is certainly contained in the 6 bytes of length, and therefore 6 bytes is fine. And if I continue to use memory locations, let's say of 6 bytes long, it means that even if I don't know the results of all my calculations, I'm sure that, based on the problem I'm managing, results will always be contained in no more than 6 bytes. It's the bit that counts. Bytes are only used to address and organize bits and take up enough space to hold results. Here we are at the first blue slide, the one that serves to take stock of what we have seen so far. I hope I haven't bored you, but as we've already said, these are not topics you need to study, you just need to hear about them. We talked about electronics, based on the main component, the transistor. We have seen that electronic uses transistors, from television to smartphones, and that a particular type of transistor lends itself to on and off values. We have seen, incredibly, that with so many bits that take on-off values, which we consider equivalent to 0 and 1, we can represent numbers. For example, the sequence of bits you see equals 15. 726. We have mentioned that by treating them as numbers, we can do arithmetic operations on bits, although we have not shown how. Let's say right away that it is a matter of building specific electronic circuits with the usual transistors that can perform operations in the same way as we do additions, subtractions, multiplications, divisions, and so on. You don't need to know how, you just need to know that in addition to the bit on-off, with transistors you build circuits capable of adding up bit by bit, calculating the carryover of 1, just like we do with the decimal system. So we came to understand quite easily how an electronic calculator works. We are not yet talking about computers, many things are still missing, but electronic calculators are now ready to supplant the analogous mechanical calculators, which were hand-cranked, and electric calculators that had an electric motor instead. Now let's try to imagine how an electronic calculator works based on the information we acquired up to this point. In the meantime, let's see how we can break down a calculator into basic components. The RAM, the memory where data will be stored. The display with its electronic circuits that manage a dedicated memory position, and any string of bits on it, is printed as numbers on the display. Let's consider the display, its electronic circuits, and the dedicated memory area as a single component. A second memory zone, made up of several predefined fields, stores everything that is typed on the numeric keypad. If you type numbers, they are transformed into bits and stored in the memory area of the display so that the user can see what he is typing. At the same time, they go to the memory area that stores the input data, as we will see in the following slides. Finally, let's imagine that there are a number of specialized electronic circuits, each of them capable to do specific arithmetic operation corresponding to the plus, minus, multiply, and divide keys. Now let's assume that the user types 5034. The data is moved in the area associated with the display, and the electronics shows the number on the display. Then the user presses the plus key, and the electronics associated with that key stores the number entered in the memory area dedicated to this function, and prepares to accept new inputs from the user. That is, a second field in the memory zone is freed up to be ready to store other user inputs. At this point the user presses 2, and as before the data is moved to the memory area associated with the display that shows the number 2. Finally, the user presses the equal key, and the number 2 is stored in the second area of the memory zone dedicated to calculations, and the sum circuit contained in the arithmetic unit, the heart of the calculator, is activated, which performs the sum and deposits the result in the area associated to the display, and the user can read 5036. About everything we have seen and heard so far, it is worth mentioning that we have been able to follow quite easily step by step how an electronic calculator works. We first broke it down into few components such as the display, the numeric keypad, the memory, and the arithmetic unit. That is, we have learned to recognize some of the basic components that characterize an electronic calculator. We already knew about the existence of transistors and electronic circuits that are used to build the RAM, the electronic memory, made up of many bits that are used to store numbers in binary format. We also learned that with transistors, we can create specialized circuits to print numbers on the display. To create a sequence of bits when certain keys are pressed on the keyboard, or that we can do mathematical operations with numbers represented in the form of bits by pressing other specialized keys, such as the equal key. We've basically figured out that there are an infinite number of circuits, based on transistors, that are used to act as bits in the RAM, to do calculations on bits, to display numbers, to receive user input. An infinity of circuits, each specialized in doing a single specific job. But given this architecture, we have seen how everything works always step by step, in a rigid sequence. We can say that we are starting to get to know a few aspects that also characterize computers. But there are still other important elements that we will see shortly. To build a calculator, you don't need the logic gates, which on the other hand are basic elements of any computer. Let's see what are they. The NOT gate examines a bit and returns its opposite state. That is, if the input bit is on, it returns off, and if it is off, it returns on. The AND gate examines 2 bits in input and returns on, only if both input bits are on. The OR gate takes also 2 bits in input and returns on, if at least one or both input bits are on. There are also other types of gates that are obtained from the combination of the previous ones. NAND is a NOT gate plus an AND gate. NOR is a NOT gate plus an OR gate, and others. With logic gates, the arithmetic unit that we saw among the typical components of an electronic calculator, the one that contained integrated circuits to do arithmetic operations, such as sums or multiplications, with the logic gates, becomes a logical arithmetic unit, which is specific to build computers. Alan Turing. The man who can be considered the father of computers and all its implementations, like artificial intelligence, the one who gave birth to the computer science. A brilliant English mathematician, he helped defeat Hitler during the Second World War by deciphering Enigma, the machine used by the Germans to encrypt and decrypt secret war messages. Alan Turing was one of the first theorists of the area of study that is now known as computer science. As a child, Alan was a very smart, lively and extremely curious child, but also very unkempt and fickle. For him, the rules were often incomprehensible, and he disobeyed more out of distraction than out of a desire to transgress. Too distracted and so unkempt that he was accused of being dirty. He lived university life in his own way, trying to have a social life within the limits of his possibilities and interests. In fact, he was a teetotaler, generally very shy and suffering from slight stuttering. Aspects that didn't help him to socialize. In 1936 he theorized an automatic machine, a kind of supermachine capable of performing calculations instead of humans. A kind of electronic brain capable of doing any kind of processing if properly equipped with the necessary elementary instructions. This allowed him to move to Princeton for a doctorate in mathematical logic. People were starting to talk about the automatic machine as the Turing machine. But what is the Turing machine? In very simple terms, Turing makes an important statement for those times. He states that any processing can be reduced to a series of elementary instructions executed sequentially by a machine. There was nothing like this at that time, and this statement might have seemed risky, yet to be proven. He was the first to imagine that it was possible to transform any calculation, any logical elaboration into a set of elementary instructions that a machine could execute in sequence. He stated that whatever the type of computation or processing is, it can always be transformed to a finite set of elementary instructions. Instructions contained in a hypothetical tape that the machine is able to read and execute in sequence, having also the ability to jump from one position to another, back and forth, based on the occurrence of certain conditions. In 1945 he carried out a machine project called the Automatic Computing Engine, but unfortunately it was rejected because of the costs. In 1948 he moved to Manchester, and there he managed to create the Manchester Automatic Digital Machine Project, whose programming system was later used for one of the first real computers, the Mark I. In 1950 he published Computing Machinery and Intelligence, an article where he talked about the so-called Turing test. He was convinced that an artificial intelligence could only be created if we would understand the functioning of the human intelligence. And he elaborated a test to compare human thought with artificial thought. Unfortunately, in 1951, by chance, her relationship with another man emerged and Turing was accused of homosexuality, which at the time was considered a criminal offense, and he had to leave all government posts. On June 7, 1954, he was found dead in bed from cyanide poisoning. The industry began to miniaturize electronic circuits more and more, managing to build apparatuses that contained thousands, then hundreds of thousands, then millions and now billions of transistors, until almost the atomic level. You are now familiar with bits, numbers in binary format. You know that on numbers in binary format we do additions, subtractions, multiplications, divisions exactly as we know how to do them with decimal numbers. You know how to deal with a series of bits by grouping them into bytes. You access them through their starting position and their length in bytes. In this way, you know how to access the memory areas and manage the bits contained in it, or store result of a calculation. You know so much about digital electronics. What are you missing to project a computer as Alan Turing imagined it? Let's try to do it ourselves. The machine that Alan Turing hypothesized is made up of a tape of finite length, divided into many slots, each containing an elementary instruction that the machine executes in sequence. In addition, in order to be able to carry out any processing, it must be possible to change the sequence when certain results occur. Instead of executing the instruction in the next slot position, the machine must be able to jump to another position on the tape and continue from there. We will use the RAM, so the tape will be a portion of our RAM and the adjoining slots will be the bytes. For the instructions, we are already able to put a logical arithmetic unit which, in addition to the 4 operations, can perform tests on the individual bits and of course on bytes. It can also copy, move the contents of memory areas, store new values in it. We still need a solution to be able to change the sequence of instructions, but this is quite simple. We just need to create an electronic circuit that, depending on the result of a previous test, instead of proceeding to the next slot, it switches to another slot and continues from there. We now have everything we need to build a Turing machine. The machine that Alan Turing hypothesized is made up of a tape of finite length, divided into many slots, each containing an elementary instruction that the machine executes in sequence. In addition, in order to be able to carry out any processing, it must be possible to change the sequence when certain results occur. Instead of executing the instruction in the next slot position, the machine must be able to jump to another position on the tape and continue from there. We will use the RAM, so the tape will be a portion of our RAM and the adjoining slots will be the bytes. For the instructions, we are already able to put a logical arithmetic unit which, in addition to the 4 operations, can perform tests on the individual bits and of course on bytes. It can also copy, move the contents of memory areas, store new values in it. We still need a solution to be able to change the sequence of instructions, but this is quite simple. We just need to create an electronic circuit that, depending on the result of a previous test, instead of proceeding to the next slot, it switches to another slot and continues from there. We now have everything we need to build a Turing machine. And that's where we made our computer project. You see the RAM in the middle, the logical arithmetic unit, and the various device controllers that are nothing more than the set of electronic circuits built to drive specific peripherals such as the monitor, the keyboard, the disks, the USB ports and so on. As we have now understood, the Turing machine executes step by step the instructions it reads from memory. The instructions say to retrieve and store data in memory, to interact with input and output devices. And all these communications must necessarily take place through connections between the various components. There is therefore a need to have a series of tracks, like highways that connect the various components to each other in a network of connections. This kind of highway is called bus. Initially it had 8 tracks, then it went to 16, then 32, and now 64. When you hear about a 64-bit PC, it means that it has a bus consisting of 64 lines, one for each bit. Of course, the more bits, the more data is transferred all at once, and the faster the execution speed is, and the higher the complexity and cost of production are. And here we are, taking stock of what we saw so far. This time, thanks to the definition that Alan Turing has given to this machine, capable of performing any type of processing, we too have been able to design it in all its components, and we have understood its operating principle. Like so many pieces of Lego, we are able to understand what RAM is. What is the logical arithmetic unit that from now on we will call CPU? As it is more commonly called, because in addition to the logical mathematical unit itself, the CPU contains other electronic circuits, such as the internal memory, registers, and the clock, which we will talk about at length later. We have also seen that unlike calculators, the computer has a set of so-called logic circuits that allow it to compare two bits with each other, and cyclically a series of bits at will between two contents of memory. Focus your attention on this last aspect, because we will find it very often in the rest of this presentation. Let's remember that the computer is able, with logic gates, to determine whether two sequences of bits are the same or different, and if different, which is greater and which is less. Pay attention to this aspect. Now that we've been able to set up our computer, let's get down to the instructions. That is, let's move from the hardware to the software. And with software, we worry more about data and information than about the logic of programs. Look at the sequence of bits depicted in the title. It occupies 2 bytes plus a single bit and represents the number 1, 2, 3, 4, 5, 6. Or if you prefer 123,456. What meaning can we give to this value? The programmer knows the meaning, only he can explain to us what it means, what importance to give it, if we should worry or be happy, or if it should leave us indifferent. Also know, just to complicate even more, numbers can be represented not only in binary format, as we have seen, but also in other formats, and here we see the number 1, 2, 3, 4, 5, 6 represented in binary format, whereas you can see, it occupies 3 bytes and in a format that is new to you, called packed or decimal, which occupies 4 bytes. So not only does a number in itself have no meaning, but if we look at memory and the sequence of bits, we don't even know what we're looking at unless the programmer tells us where and how to look. Maybe you didn't think that for any computer this is the reality. But we can also memorize characters, images, sounds. Also in digital format, i.e. with bits. And in these cases, how to represent a character of the alphabet. The so-called transcoding tables are used. I mean, each character is conventionally matched to a number, and so the value 65 corresponds to A, 66 to B, and so on. Just to please you, there are 2 standard tables. One is internationally accepted, the ASCII table, and the other is coined by IBM. There are also various formats for images, but conceptually, once you have established how many bytes you want to use to describe a pixel on the screen, you have areas of memory where each group of bytes contains color, intensity of the corresponding pixel of the monitor. The more bytes you use for color, the more variety of shades you can store and the higher the image quality. For sound, the intensity of the sound wave is stored for each fraction of a time. We'll look at this graphically later when talking about artificial intelligence. For now, remember that the data in RAM is incomprehensible, except for the programmer, who wrote the software that produces and manages it. The first part of this long explanation on how computers work ends here. We are taking a break for now. You can reflect if you want on the things you had the opportunity to listen to and to learn. We repeat it once again. You do not need to completely understand everything we have told you. Because, as you will see in the second part of this presentation, with the notions that you got from this first part, you are already able to project your first program, your first software app, I know you don't know any programming language, but this first part, even if you didn't realize it, has already given to you everything you need to know to design a program, and even if you don't believe it, you can verify it as soon as we return to the second part, which will deal with the software.